Reflections. Reflections occur in everyday life. We see them through reflections in water, as these two show, or reflections in a mirror.
A reflection, or flip, creates a mirror image of a figure. It is a transformation that preserves the size and the shape of the figure. Therefore, both the pre-image and image will be congruent. Congruent figures are the same size and shape. They have equal side lengths and corresponding angles that are equal in measure.
A reflection or flip creates a mirror image of a figure. So if our original figure is right here and we reflect it across the line, we get this image that appears over to the right. A reflection is a flip because the figure is flipped over a line. In this diagram, it's line T. Each point in the image is the same distance from the line of reflection as the original point. So if we notice point C, we had to go 1, 2, 3 spaces to get to the line of reflection, so we have to do the same thing on the other side. 1, 2, 3. Point A, we have to go over 1, 2, 3, 4, 5, 6. So let's see if it's another 6. It should be 1, 2, 3, 4, 5, 6. Yes, that gives us our A prime. So it does show us that A and A prime are both 6 units from the line T. Points B and B prime are also 6 units from line T, and we counted and showed that points C and C prime are both 3 units from line T. Each vertex in triangle ABC is the same distance from line T as the vertices in triangle A prime, B prime, C prime. When a reflection occurs, are the line segments and angle measures in the pre-image and image congruent? In other words, was the size of the figure preserved through reflection? Take a moment to pause this video and think about it, and when you're ready for the answer, unpause it. If we look at our original triangle, triangle ABC, and triangle A prime, B prime, C prime, yes, both of these triangles are congruent to one another. Any perpendicular line segments remain perpendicular, is one example. Since AB is perpendicular to segment BC, then segment A prime, B prime is perpendicular to segment B prime, C prime. So because all of the angle measures and the slopes of the lines are preserved and the distances from one point to another are all preserved, reflections allow for diagrams or pre-images and images to remain congruent. Reflect the figure across the y-axis. Let's start examining and reflecting using point A. So from point A, we need to go 1, 2, 3, 4, 5, 6 spaces to get to the y-axis. So we have to go another 6 spaces. 1, 2, 3, 4, 5, 6. So this is going to be where point A prime is going to be. Now let's look at point B. We have to go 1, 2, 3, 4 spaces to get to our line of reflection. So we have to go 4 in the same direction, continuing 1, 2, 3, 4. So here's where B prime is going to be. Now for C, we have to go 1, 2, 3, 4 units to get to the line of reflection. So we have to go another 4 units. 1, 2, 3, 4 to get our new point C prime. Now let's look at D. So for D, we have to go 1, 2, 3, 4, 5, 6. And we have to do 6 again. 1, 2, 3, 4, 5, 6. And we have D prime. And now we can connect all of our points with line segments to create our trapezoid A prime, B prime, C prime, D prime, which is a reflection of trapezoid ABCD across the y-axis. The reflection of trapezoid ABCD across the y-axis is shown below to give us trapezoid A prime, B prime, C prime, D prime. What do you notice about the coordinates when a figure is reflected across the y-axis? How can the problem be represented by symbols and numbers? Well, let's actually see. For point A, it is at -6, 5, and point A prime, so A, -6, 5, and then A prime is 6, 5. Now let's look at point B. Point B is at -4, 5, and B prime is at 4, 5. All right, point C is at -4, 1, and C prime is at 4, 1. And the last one, point D, is originally at -6, 3, and D prime is at +6, 3. So what do we notice about our coordinates when we go from the original points to the new points? Well, the y-coordinates 5, 5, 1, and 3 remain the same, and the x-coordinates become the opposite. And we can write that as x comma y goes to -x comma y. The x-coordinates switched their signs and became the opposite, and the y-coordinates remained the same. And this slide shows the solution that we did find on the previous slide. We went from -6, 5 to 6, 5, -4, 5 to 4, 5, and so on. And we found that when a figure is reflected across the y-axis, the x-coordinate becomes the opposite and the y-coordinate stays the same. In symbolic terms, that is saying that x comma y becomes -x comma y. Reflect the figure across the x-axis. Okay, so now let's count and see how far each point is from the x-axis and do the same point or the same distance from one side on the other. So let's start with point A. We have 1, 2, 3, 4, 5 to get us to the x-axis, so we have to go 5 again. 1, 2, 3, 4, 5. So this will be A prime in this case. Let's go with B. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, here's point B prime. Now C, we only have to go 1 to get to the x-axis, so we have to go 1 again. This will be C prime, and then D, we have to go 1, 2, 3. So let's do 3 again. 1, 2, 3. Right here is point D prime. So if we connect all of these together, we will have our trapezoid image A prime, B prime, C prime, D prime. The reflection of trapezoid ABCD across the x-axis is shown below. What do you notice about the coordinates when a figure is reflected across the x-axis? How can the problem be represented by symbols and numbers? Well, let's first write down the original and new coordinates of our points. So the original point A is at -6, 5, and point A prime is still at -6, but now it's at -5. -6, -5. Okay, point B is at -4, 5, and point B prime is at -4, -5. Point C is at -4, 1, and point C prime is at -4, -1. And our last point, point D, is at -6, +3, and point D prime is at -6, -3. So what do we notice about these coordinates? Well, if we look at our x-coordinates in both the original and the new, or the pre-image points and our image points, they stay the same. So xy goes to, we know x stays the same, but then we have, in our original, we have y coordinates of 5, 5, 1, 3. They became -5, -5, -1, -3. Oh, all the y coordinates became the opposite, or -y. So xy became x -y. And this is the solution to this example as to what happens to the coordinates. It does show a prime, b prime, and so on that we had found. And we notice that when a figure is reflected across the x-axis, the y-coordinate becomes the opposite, or y became -y, and the x-coordinate stayed the same. X went to x again. So again, x comma y goes to x comma -y, where the x-coordinate stayed the same and the y-coordinates became opposites. Reflect the figure across the y-axis and then the x-axis. Okay, let's go through doing that. So first we'll do the y-axis, and we'll start at point A. So we have 1, 2, so we have to go 2 again. So this is where the point A prime will be. Now let's go for point B. It has to go 1, 2, 3, 4 to get to the y-axis, so we have to go 4 again on the other side. 1, 2, 3, 4. So here's B prime. C, we have to go 1, 2, 3, 4. So we have to go 1, 2, 3, 4 again to get to C prime. And then for D, we have to go to the right 1 unit, so we have to go another one to the right. So this is where D prime will be. And then if we connect these, we will get the first diagram that we have for the reflection across the y-axis. Now we have to reflect it again, but have it reflect across the x-axis. So first we reflected it across the y-axis. Now we are going to reflect this one across the x-axis. So let's start at point A prime. We have to go 1, 2, 3, 4, 5, 6 down. So we have to go 6 down further. 1, 2, 3, 4, 5, 6. This is going to be the point A double prime. Now if we do the same process with point B prime, we have to go 1, 2, 3, 4, 5. So we have to go another 5. 1, 2, 3, 4, 5. So here is point B double prime. Point C prime, we have to go down 1. So we have to go down 1 again to get C double prime. And then for D prime, we have to go 1, 2 to get to the x-axis. So we have to go 2 again. And this is going to be where D double prime is going to be. And then if we connect them with our line segments, we will get the final image after the reflection across both the x and y axes. Across the y-axis first and then the x-axis second. All right, so the reflection of quadrilateral ABCD across the y-axis and then the x-axis is shown below. And it does generally match the diagrams that we had created when we drew it out ourselves. What do you notice about the coordinates when a figure is reflected across both the y-axis and the x-axis? In other words, what's the relationship between the coordinates from quadrilateral ABCD to quadrilateral A double prime, B double prime, C double prime, D double prime? So let's actually see if we can find that relationship. So point A is at 2, 6, and A double prime is at -2, -6. Okay. Point B is at 4, 5, and point B double prime is at -4, -5. Okay, point C is at 4, 1, and C double prime is at -4, -1. Point D is at 1, 2, and point D double prime is at -1, -2. So we went from 2, 4, 4, and 1 to -2, -4, -4, and -1. Our x-coordinates from our original point became opposites. And then let's look at our y values. We went from 6, 5, 1, 2 to -6, -5, -1, -2. So all of their signs switched too. So for a reflection across both the y-axis and x-axis, xy goes to -x, -y. So we wrote down the coordinates of our original points and our double prime points. And we noticed that when you reflect across the y-axis and then the x-axis, both the x and y coordinates become the opposite of the original point. In other words, xy goes to -x, -y. Does this xy to -x, -y rule match the same rule for another transformation? If so, which one? It actually does match another transformation. And I'm going to start drawing lines through the origin so that we can see it. From C to C double prime, we drew a straight line. From A to A double prime, we draw a straight line. Same with B to B double prime and D to D double prime. This means that we have a 180-degree rotation about the origin. And it doesn't necessarily matter the order or the direction in which you rotate 180 degrees, since 180 degrees clockwise will be the same as 180 degrees counterclockwise. So this xy to -x, -y rule is equivalent to the rule for a 180-degree rotation. And again, we can draw the lines connecting these to show that 180-degree rotation. And this means that a 180-degree rotation can also be obtained by reflecting the original pre-image across both the x and y axes, and in either order. If you actually reflected this across the x-axis and then the y-axis, you would still end up at the same exact A double prime, B double prime, C double prime, D double prime quadrilateral. Reflect the figure across the line y equals x. Let's actually start by drawing this line in. I'm going to try to separate it from what we've been doing, and I'll try to make it a little bit thicker so that we can see it. Okay, so here's our point y equals x. And then to distinguish it from the others, I'm also going to make it dotted. Okay, so here's the line that we're going to reflect this rectangle about. So notice D actually lies directly on this line, so D prime is going to be that same exact point. Now if we look at point A, I have to go diagonally down one to get to this line, so I have to go diagonally down one again, so this will be where A prime is. Okay, for B, we have to go 1, 2.5, so here's the other half, and 1, 2. This will be where point B prime is. And then for C, we have to go 1, 2, 3.5. Here's the half, 1, 2, 3. So here's where C prime will be. And if we connect these to make a line, or connect them with line segments, we'll get this rectangle that looks like this. The reflection of rectangle ABCD across the line y equals x is shown in this graph below. What do you notice about the coordinates when a figure is reflected across this line y equals x? How can the problem be represented by symbols and numbers? Well, we know that point A was at 2, 4, and point A prime is down here at 4, 2. Now let's look at point B. Point B was at 9, 4, and point B prime is up here at 4, 9. Point C is at 9, 2, and C prime was at 2, 9. And our point D was at 2, 2. And point D prime actually stayed in that same position, 2, 2. So what's the relationship between 2, 4 and 4, 2? 9, 4 and 4, 9. 9, 2 and 2, 9, especially. Point D doesn't really help us as much because all of these numbers are all the same. But what happened here? Well, if we start with our original coordinates x, y, didn't they switch positions? Like the y became the x and the x became the y? Yeah, they did. I went from 9, 4 to 4, 9, so I wrote it as y, comma, x. No signs changed or anything like that, just the numbers switched positions. So what we have is we have the coordinates of points A, B, C, D, and A prime, B prime, C prime, D prime. And what we found was when you reflect points across the line y equals x, the x and y coordinates end up switching positions. No signs change. You just have x comma y become y comma x, as this formula shows, and we can verify it. X is 9, y is 4. So we switch them around, y comma x, 4 comma 9. And it happened with every single point. It's a little harder to see with D and D prime because they were 2's in both the x and y coordinate positions. Reflect the figure across the y-axis. Okay, so we have A here. It is actually on the y-axis, so A prime is going to be that same exact point. For B, to get to the y-axis, we have to go 1, 2, 3 units. We have to do the same thing on the other side, 1, 2, 3. So this will be for B prime. And then for C, we have to go 1, 2, 3. So we got to do the same thing, 1, 2, 3. And then for D, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So actually what I'm going to do is I'm going to relabel C prime. There we go. Now for E, we have to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then for F, we just have to go 1 to get to the axis that we're reflecting about. So we have to go 1 in the other direction. And if we connect these with our line segments, we will get the same figure just reflected across the y-axis. And the solution on this slide does verify that the image of our original figure after being reflected across the y-axis is this shape right here, A prime, B prime, C prime, D prime, E prime, F prime.